Hi everyone, thanks for attending my talk. My name is Benjy. I'm one of the core contributors to the Pants open source build system. And today I'm going to be talking about how we used some cool Python features in fairly unorthodox ways to create the extensible workflow system that is the core of the Pants system. And hopefully this may give you some ideas about how you could use similar techniques in your own systems. Before we get started, just a little about me. I have a fair amount of experience as a software engineer, and many of those years involve working on build systems. I've had the good fortune to work at a bunch of cool companies. I am, as I mentioned, one of the maintainers of the Pants open source project, and I am now the co-founder of Toolchain, which is a startup in the build system space. So let's jump right in. So first up, what is a workflow? So when I say workflow, I'm talking about a sequence of tasks that processes data to produce a desired result. And that's a fairly mundane definition. I mean, if you think about it, that doesn't even require computers to be involved. And in fact, there is a whole category of software devoted to managing workflows where the tasks are performed by humans. So, for example, the workflow for onboarding a new employee, the actual tracking the tasks could be done by a computer, but the tasks themselves are done by people. But for the purpose of this talk, we're more specifically talking about fully automated workflows where the tasks themselves are just computer processes. And those workflows show up all over the place. There are so many examples. I've just listed a handful of them here. But to give a little flavor of what I'm talking about, let's look at a very simplified example of a workflow for processing uploaded images. And again, very oversimplified just to make a point. So as you can see, we have some image data that's being uploaded along with its file name. And then we have some tasks that run to operate on that data, and the end result is a database entry containing an image that we can then use. So again, very oversimplified, but even in this simple example, there are some instructive things to pay attention to. So one thing to notice here is that the workflow consists of a set of tasks. Each one is performing some small self-contained action. Each task has a set of inputs and an output. There are dependencies between these tasks, so a task can require as input the output of some other task, and that imposes a dependency relationship, which form edges in this graph. Now, there's a set of initial inputs to the entire workflow. Those are the nodes colored in green in this diagram. And there is a final output to the entire workflow, which is the node colored in blue in this diagram. And so the workflow is literally a flow through a graph of tasks. And that kind of structure where you have a set of tasks and dependencies between them and a set of initial inputs and a final output, that's pretty much the structure of workflow that we are going to carry through the rest of this talk. So kind of bookmark that in your mind. So as I mentioned, workflow is defined by a task graph, which is a directed acyclic graph in which the vertices are tasks and the edges are these direct data dependencies. So to form this graph, we need a set of functions that perform relevant tasks for the problem domain, so image processing in that example. And we need some knowledge about inputs and outputs and how they all map to each other. And it's important to note that at runtime, there may be many task instances invoking the same function code. So for example, we probably created that image processing workflow to process many uploaded images, each in the same way, using the same functions, but on different input. So a task at runtime is not just a function, but a function in the context of a set of initial inputs. Again, bookmark that in your mind. And that brings us to the challenges of designing a system for running workflows. And specifically, we're going to talk about designing a task API. So any non-trivial workflow system is going to need to give programmers a way to define the tasks that it runs, those functions. And that allows you to extend the system and add new logic and plug it in. And the motivating example of this for the rest of this talk is software builds. So, as I mentioned, Pants is this scalable software build system. It has a design emphasis on user-friendliness, and it implements a workflow in which the workflow engine, which actually sequences and runs the tasks, is implemented in Rust, and that's primarily for performance reasons. But the tasks themselves are implemented in Python because Python is a well-known, fairly simple language that is a pleasure to write business logic in. So we're going to look at how we designed the task API for Pants by leveraging some Python features in some interesting and unusual ways. Now, when I talk about a workflow for software builds, just to clarify, the tasks are build steps such as running a linter or running tests or compiling code or building a package and so on. You can think of many dozens of examples like that. And it's also all the tasks along the way. So there can be actually hundreds of these little tasks that do various self-contained bits of work in the system. And dependencies in a workflow for software builds are what you would expect they would be. So, for example, to run a test, we first need to compile it if we're dealing with a compiled language. Or, in a more Pythonic example, to type check a file, we first need to resolve its dependencies. And so the tasks that do dependency resolution have to run first. So if you think back to the diagram I asked you to bookmark in your mind, there was also the concept of initial inputs and final outputs. And so in this example, the initial inputs are things like source files on disk and any configuration to the build system. And the final outputs depend on what the user asked for on the command line. So for example, if the user says, show me the results of running these tests, then that creates a different final output to if the user said, I want to build a wheel for this package. So the flow through the graph will be different depending on what the user asked for, but the context of the initial inputs are things like the source files on disk in general, and specifically the ones the user asked to act on, and so on. So we have in our minds what a workflow for software builds roughly looks like. We've defined what are the vertices and the dependency edges in the task graph. We've talked about what the initial inputs are and what the final outputs are. So when we came to design the workflow engine for Pants, we had a set of design goals in mind, and you can see them enumerated here. Now, the first 4 of these design goals are really driven by performance concerns. It's very important that as your code base grows, you keep your build fast and stable. And there are really 2 ways to do that. One is to do less work, and the other is to do more of the work at the same time. So to do less work, you need tasks to be fine-grained so that on changes, less of the work gets invalidated. And you want caching so that you don't repeat work that's been done before, either by you or by someone else on your team. So those first 2 design goals are really driven by the need to do as little work as possible. The second 2 design goals are driven by the need to do more work at the same time. You need concurrency support so you can know when 2 tasks can run in parallel because they don't depend on each other. And you would like to have remote execution so that you can actually run more than a handful of tasks in parallel. I mean, running, say, 8 tasks in parallel on your laptop because you have 8 cores is great, but running 100 tasks in parallel, obviously a lot better. So those first 4 goals, again, driven by performance concerns. But that last one is really a must-have. Extensibility is really important because there are so many possible build tasks, multiple languages, multiple underlying tools that can be invoked, multiple frameworks, all the in-house custom build steps that various organizations might have. We need it to be really straightforward to add task logic. So those first 4 design goals pull us towards complexity in the name of performance, and then that 5th one tugs us back towards simplicity because we want it to be straightforward to write task code. So to achieve these design goals, they imply some important constraints. So for example, tasks cannot interfere with each other, and they can neither cause side effects nor rely on side effects. Particularly, this relates to the file system. A task can't rely on some previous task having written a file to some, well-known magic location, because maybe those 2 tasks aren't even running on the same machine. But we still, for extensibility, want tasks to be straightforward to write. So we needed to find a way to balance these fairly strict limitations on the one hand without sacrificing the flexibility and the ease of use of a sensible task API. And this is where Python comes to the rescue. It turned out that Python has some powerful features that we were able to leverage and use in unconventional ways to find an interesting sweet spot of achieving those design goals without sacrificing ease of use by too much. So the features that the Python features that we are specifically referring to are type annotations, async IO, and data classes. And so now let's dive in and have a bit of a closer look at how we put those features to use in novel ways. And we'll start with type annotations. So we are going to start by introducing just a little bit of extra terminology. So remember, again, I asked you to bookmark this in your minds, that we distinguished between static task functions and their dynamic runtime invocations in the context of some initial inputs. So you remember we can invoke the same functions many times on different inputs. So just to avoid confusion, we refer to the static function as a rule, and the runtime invocation of a rule is a task. So the core definition of a rule is a pure function that maps a set of statically declared input types to a statically declared output type. And how do we statically declare types in Python? We use type annotations. And so here's an example of a task definition in the Pants Task API. So you can see that this is a fairly normal looking Python function. The @rule annotation has to do with registration, and we can just ignore it for now. The more interesting thing to note here is that all the inputs to the function are type annotated, and it declares the type of its output. And the example here is a simplified version of the function that takes a file containing Python tests and some configuration and runs PyTest on that test file and yields a test result. So, given a set of rules, we can construct a rule graph by introspecting those type annotations. So we can say, well, there's a dependency edge from B to A if B has A's output type as one of its input types. And this is related to, but a little bit different than the task graph, which we talked about earlier. The task graph is dynamic. It maps between invocations of functions in the context of a specific initial input. The rule graph here is static. It maps types, not instances of those types. But that allows us to statically validate the rules and make sure that there's no ambiguity and that all the rules are reachable, and that all of the queries you might want to run through this workflow system are satisfiable. And of course, you can just write your own rules and plug them in, and you don't need to wire them in. So an interesting point here is that the names of the rules, the names of those functions, are immaterial because rules don't reference each other by name. The workflow system itself knits together the call sequences by analyzing transitions from here's a set of types that I have to here is a type that I need. So those names are just used to provide helpful error messages. And in case this feels familiar, this is basically dependency injection. So it's similar in some ways to, say, you may be familiar with fixture injection in PyTest. The difference is that PyTest does fixture injection by name, while here we do it by types. And so this knitting together of all of these rules without having to make explicit calls from one to the other is enabled by unconventional use of standard Python type annotations. And you may ask, well, what's unconventional about it? If you think about the purpose of type annotations, they exist primarily to make code more readable and to support, like MyPy, to support static type checking, which helps enforce the correctness of your code. So they are metadata about your code that helps with the craft of programming. But we're using the type annotations as an actual runtime language feature that for purposes that have nothing to do with code hygiene or code correctness. So we've seen how of those 5 design goals that we had, type annotations, when used in this unusual way, provide us with fine-grained tasks, and they provide us with extensibility. You can just write these functions, provide type annotations, add that @rule annotation, and you're good to go. The system will plug it in the right place for you. So having talked about type annotations, let's move on to async I/O, a major Python 3 feature. So here, I need to admit that I cheated a little for didactic purposes on my previous definition of a rule. It's actually not a pure function, it is a pure coroutine. So same definition as before, but we now emphasize that the rule is a coroutine, and this means that it can yield back to the workflow engine in mid-execution. So the definition is identical to the one before, except you see the use of the async keyword. And what that enables is that as a rule runs, if it realizes at runtime, based on inputs that are only available at runtime, that it needs some extra input, it can yield back to the workflow engine. So you can see this standard await async I/O syntax. One important thing to note here is that the thing that you await on is this object called a get, which is a type in the system. And you can't await arbitrary Python awaitables. And the reason for that is that the event loop that is implied by the async I/O paradigm is run by that Rust engine that I mentioned and not by the async I/O run. And so if you were wondering, well, what is off-label about this? The answer is we're using the async await syntax, but we're not using the standard async I/O event loop. We're actually running an event loop from outside of Python entirely. But because Python is so good about letting you introspect it, we can use the async await as interaction points between Rust and Python in a way that is transparent to the author of these rules. You just write fairly idiomatic async I/O code. Now, coroutines are very powerful because, as I mentioned, the rule application, the path through the graph, is determined dynamically on the fly rather than statically, that means you can use runtime information to inform how the build will unfold, but you still get that static checking. Being able to yield back to the engine sort of at runtime means that you can apply a natural control flow. So you can do things like looping and branching, but still have this static validation. But even more importantly, coroutines make it easy for you to express concurrency. So if you look at this little code snippet, now we're not awaiting a get, we're awaiting an entire iterable of gets wrapped in a thing called a multi-get. And the engine will execute these concurrently. And because the engine is implemented in Rust, and so outside the global interpreter lock, these will frequently execute in parallel. Like these can execute with, particularly if they involve things like I/O and process execution, then they will actually execute in parallel. The other great thing about coroutines is they help us avoid side effects. So for remote execution, for example, to work, as we mentioned, rules cannot have side effects and they cannot rely on side effects. So it's important that you don't make system calls, you ask the engine to make them for you so that they can do it in a safe manner. So for example, you can see an example here of instead of just directly accessing the file system, you await for an object called a snapshot that represents a little portion of the file system, and the engine presents that to you. Or instead of running processes directly using the subprocess module, you again yield back to the engine and say, please run this process for me, and it will return a process result. So you're probably realizing that there have to be some side effects because otherwise the user gets nothing. So the outermost rule that computes the final result is allowed to have certain side effects. So it can emit to the console, or it can write results to local disk. It can actually do the side effecting that is the thing the user asked for in the first place. But extra special care is taken that those side effects are always replayed, even if everything leading up to them, say, was satisfied from cache or run remotely. So we've seen that this unconventional use of coroutines provides natural control points for concurrency and for remote execution. Which leads us on to data classes. So this is all about cacheability. For caching to work, rule input types have to be immutable and hashable, and I think it should be fairly obvious why that is the case. You have to be able to compute a key, and you have to know that that key always refers to equal objects. And Python has an out-of-the-box solution for this, which is frozen data classes. So here's an example of a frozen data class that represents the configuration that you need for running PyTest at a certain version with a certain set of plugins. It's really trivial to make this type cacheable, and so frozen data classes are ubiquitous throughout the API. And all of those input and output types that you annotated earlier, those just have to be frozen data classes. And simply by requiring that, we get well-defined fingerprints for all these runtime tasks, which allows caching to work. And what's off-label about this? Well, to be honest, nothing. Data classes are just very cool and an absolutely wonderful way to avoid boilerplate and bugs, and I really wanted to show how we use them to great effect. So, as we've shown, using data classes and async I/O and type annotations together in ways perhaps beyond those they were directly designed for gives us a powerful framework and a powerful API for building extensible workflows. We've achieved all of our design goals here. So, I think this is a testament to the design of Python 3. Python 3, particularly recent versions, really occupies a sweet spot on the simplicity versus power trade-off curve, and we were able to leverage that to hopefully occupy a similar sweet spot on the simplicity versus power curve in our system, where you write fairly idiomatic async IO Python code, and complicated things like caching and concurrency and remote execution just fall out of the system, and you don't have to do anything special as a rule author in order to get them. So I want to thank you so much for listening. I'm happy to take any questions, and you can find us in Startup Row. You can find my company there if you would like to virtually swing by. And of course, you can find out more about the work that I've talked about at this URL. So thanks again.